So we're looking at the University of Washington's Math 120 pre-calculus course. We're considering the fifth question on midterm 2 from winter 2016. And the first part of this question asks us to consider the human population of Seattle. We have a function f which models the population of Seattle t years after 2010. So the problem tells us that in 2010, the population was 500,000. We've interpreted this as f of 0 is 500,000. In other words, 0 years after 2010, the population is 500,000. And the population decreases 3.7% per year. And we're asked to write a model for f. Go ahead and pause the video now and see whether you can write a function that will model the population of Seattle given the data we have. Okay, so let's take a look at it and see what we can do. I hope you notice that f is going to be an exponential model. The fact that we're working with populations should have maybe given you a little bit of a clue, but the real detail that makes us sure that this function is in fact exponential is this idea that the population is changing by the same percent each year. So we're going to have something that works more or less like this. This is a typical form of an exponential function. There's a couple of different standard forms for exponential functions. Let's see what we can do with this one. Notice that if I plug in t equals 0 to this equation here, I find that 500,000 equals, well, this b to the 0 term falls away, and I have that this coefficient here, this a, is 500,000. In fact, I can really write down this model almost from scratch, just as 3.7% decrease is the same as 96.3% of the. So notice how this works. When I plug in t equals 0, I get 500,000 times 1. When I plug in t equals 1, I get 500,000 times 96.3%. And when I plug in t equals 2, I get 500,000 times 96.3% times 96.3% again. So we can see quite explicitly that this function does model the population of Seattle. So the rest of this question asks us to consider bees in Seattle and the relationship between the numbers of bees and the number of people. Okay, so we have this information about the bee population. We have that the population of bees is growing exponential, and it's modeled by g of t. Again, here t is years after 2010, just as it was before. And we know that in 2014, there are the same number of bees as people in this town. And in 2025, there will be 3 bees for every person in town. In general, to write an exponential model, all we need is 2 data points. So here we have 2 data points. We know more or less a population in 2014 and a population in 2025. That's all we're going to need. So what do we get out of these? We have g of 4. This is the population of bees in 2014. Is equal to the population of people in 2014. And what is f of 4? Well, it's 500,000 times 0.963 to the 4th. And I also know something about the year 2025. That's 15 years after 2010. The bee population in 2025 is 3 times the human population in 2025. In other words, it is 3 times 500,000 times 0.963 to the 15th power. So let me grab a calculator and actually compute these numbers. G of 4 equals 430,007. I'm going to actually keep some decimal points just for sake of care. And let me also compute G of 15. G of 15 I find to be 852,090.19. So I have G of 4 is 430,006. I have G of 15 is 852,090. Given this data, I can really just write down the solution quite explicitly. So what I find is that G of t is going to be equal to some coefficient here times some base here to some exponent here. I'm going to choose the exponent to behave in a kind of peculiar way, or a kind of clever way, maybe. I'll choose the exponent to behave in such a way that when I plug in t equals 4, my exponent becomes 0. And when I plug in t equals 15, my exponent will become 1. So let me write this out. I have t minus 4 works when I plug in t equals 4. But right now, when I plug in t equals 15, I get 11 here. So I'll divide this by 11. And now I have an exponent that behaves just as I described. So when I plug in t equals 4, this becomes an exponent of 0, which means that this falls away. And I'll just write this as 430k. This is for 430,000. This is not a variable here, just for fitting it on my page here. This behaves now nicely when I plug in t equals 4. But when I plug in t equals 15, this exponent just becomes 1. So if I write now 852,090 over 430,000, then things behave quite nicely. Notice now that when I plug in t equals 4, I get 430,000. And when I plug in t equals 15, I get 430,000s cancel, and I get this 852,000. So here is my solution. Of course, this 430,000 and 852,000 should actually be these more exact numbers. The very last part of this problem asks us to find when the population of bees will be 5 million. So in particular, we can simply set the left-hand side of this to be equal to 5 million. I'm using K's and M's to abbreviate thousands and millions. I need to solve for t here. So let me first divide both sides by 430,000. Now, if I want to solve for t, I need to get the variable out of the exponent. What's my trick for getting variables out of exponents? I'll hit both sides of the equation with a logarithm, and any base will do. So I'll hit it with just a standard log base 10 and write this as. And now why is this helpful? Well, when I hit this with a logarithm, I get to bring this exponent out front. And I can write this now as t minus 4 over 11 times the log So from here, we can solve for t quite explicitly. We can simply divide both sides by this term, then multiply by 11 and add 4. And we find that t will equal the log over here over this log, and then we multiply by 11 and add 4. And this is our solution for when the total population will be 5 million. So if I had a calculator in my hand at this point, I would actually compute a particular value of t and plug it back into my equation g of t here and check whether this does actually give me a value of 5 million.